Hello everyone. This is going to be the chapter 3 lecture notes. This chapter is about motion in one dimension, and basically is just a definition of what velocity and acceleration is and how position slash velocity change with regards to constant acceleration. So if you have uh done a calculus course, which I'm pretty sure is required here, this shouldn't be too big of a deal because it's basically just defining what a derivative is. And then the only thing you have to look out for are kinematics equations, which are pretty simple to derive if you have an ideal of calculus. And other than that, it shouldn't take too long. So I'm just going to go through the derivations for what velocity is, what acceleration is, what the kinematics equations are, where kinematics means how an object moves uh, with respect to acceleration and velocity and position. Uh, so yeah, it shouldn't be too difficult. The first thing that we're going to define is called displacement, where displacement is a vector, which in this case is one dimensional. So it's x minus x initial, where x is your position in space and x initial is your initial position in space. So for example, if you have an origin here, and this is your position, this is how far along you've walked on it. If you start out 1 meter out and you end up 6 meters out, then your displacement is going to be from this initial 1 meter for the tail to the 6 meters for the head of the arrow, and that's going to be equal to uh, that's going to be equal to 6 meters minus 1 meter equals x minus x naught because it's your final position minus the initial position. And then the displacement is going to be equal to 5 meters. So it's pretty simple to do. You could also have the opposite happen where instead of going from the left to the right, you go from the right to the left with the x-axis still being defined to be to the right. So if you do that from 6 meters to 1 meter, then the displacement equals x minus x naught equals 1 meter minus 6 meters equals negative 5 meters. So yeah, that's pretty simple. The negative sign lets you know that it's a vector because it can have positive or negative values. But the it's a vector in one dimension, so we just define it as in the positive x or the positive y direction, or the positive z direction if you want to, or whatever direction you want to point in. You just have the positive and the negative direction of your unit vector. So that's displacement, but there's another value which is called a scale, the distance traveled. And I don't know if they actually uh, define, I don't think that they define it as like a particular variable or particular definition, but the distance traveled is just the length traveled. So it's a scalar and it's the absolute value of x minus x naught. So no matter which way it's going, um, both examples have the same distance because both examples you walk 5 meters, but you go -5 meters in one way and +5 meters in the other way. And that's going to have the same distance even though you're going in opposite directions. So if you uh for example, if you go out 12 meters, let's just say it's from the origin. If you go out 12 meters and then you go back 10 meters, then the total displacement is going to be equal to x final minus x initial, which is equal to you end up at 2 meters from your initial position. So this is going to be equal to 2 meters minus 0 meters equals 2 meters. But the distance traveled is going to be the absolute value of this vector, this first displacement vector that you traveled along. So 12 meters uh, plus the absolute value of this negative displacement vector you traveled along 10 meters. So that's going to be equal to 12 meters plus 10 meters. So that's going to be equal to 22 meters, even though you ended up in the around the same place. So for example, when you're doing when you go around a track, you start out by your car, you start out wherever the entrance is, and then you go in a circle over and over again, just racking up miles of distance traveled, but the displacement is going to be zero because you end up in the same position that you started out as. So as the displacement is a vector and it tells you information about where you end up in respect to your initial position, and it can be the sum of a bunch of displacements. So first you go out, then you go back in, then you go out, then you go back in, then you go out, then you go back in. Those are all displacement vectors, and you sum those vectors. But the distance traveled is the absolute value of that displacement. So the average, so that's just basically the distance or the difference between displacement and distance. So a vector quantity and a scalar quantity. But what we need to do is find the velocity, which is the average displacement. So the average velocity is equal to the average displacement over the change in time. So this is going to be equal to x minus x naught over t minus t naught, where t naught is the initial time and t is the time that you're looking at. So V equals displacement over delta T. Delta means change in. It's just a mathematical formula that we use. Equals x minus x naught over t minus t naught. So this, and then this bar over here, this straight line over the V means that it's the average value. So V equals x minus x naught over t minus t naught. The average value of velocity is x minus x naught over t minus t naught. But this is going to run into the same problem we were talking about, or the same weirdness. It's not a problem, it's just a way that we define it, that we were talking about with the dis or with the displacement versus the distance traveled, where if you go out and then come back in, then it's going to look like you traveled a very small displacement over a very long time. So the velocity, the average velocity is going to be, let's again define this as 2 meters and this is 12 meters. How far you went out is going to be equal to 2 meters over, let's say, 1 minute. That's very, very slow, even if you are talking about 12 meters, and or a total of 22 meters. But 2 meters over 1 minute, which is going to be equal to 2 meters per minute, which is very, very slow, but that is your average velocity over the given time. Uh, and then that's going to be like, even though you went out very far and you came back, you went your total displacement wasn't very much, so your average velocity isn't going to be very much. Now, by contrast, speed is equal to the distance traveled. I don't think they come up with a variable for this uh in the textbook, but I'm just going to say it's distance over 1 minute, which is going to be 22 meters, as we uh derived earlier, over 1 minute. So 22 meters per minute, which means that the actual speed that you were going at over the time uh is going to be about 22 meters per minute, which is about 11 times, or it is exactly 11 times faster than your average velocity. So the average speed is 11 times faster than the average velocity because velocity is a vector and speed is just a scalar adding up all the distance that you've traveled. So this is all well and good. Like, this is something that is useful, but doesn't tell you much. Your average velocity isn't going to tell you much about uh, what it looks like in the second to second of the race, or you're walking along the road or whatever you're doing. So uh, instead of having average velocity, we define instantaneous velocity. So v instantaneous is still a vector, but it's defined as the displacement of t plus delta t minus the displacement of t over delta t. So this is so far the same. Uh, this is the same equation as displacement over delta t so far. It's just saying this is the displacement of time plus a little bit of extra time, delta t, minus the displacement or the position of x of t, which is giving you is the same thing as delta x over delta t. So it's the same thing right now, but what we do in order to uh, make this instantaneous rather than just the same definition is we take the limit of delta t goes to 0. So we make it that change in velocity as small as possible, so that or that's change in time as small as possible, so that we get the slope of the line, we get the displacement over time of that instantaneous moment rather than the overall slope of the line or the overall velocity of a long moment. So graphically, what this means is if we have displacement and time, and say it looks something like this, then uh the average displacement is going to give you some value here versus some value here. So it's going to be delta t, uh, and then the velocity equals the slope of that line. So I'm not saying anything new here. I'm just talking about uh, what a derivative is. So if you took calculus, which I'm pretty sure is a prerequisite for the class, this entire discussion should be redundant towards you. But just in case, I'm going to talk about v being the slope of the line. Um, if this is the time that we're looking at, then this is some delta t, some big delta t, and this is going to give us the slope of the line from t plus big delta t through t minus big delta t. And then you can just keep getting similar things happening, where v is the slope of the line from some smaller delta t. And eventually, what happens is that you find delta t goes to 0, and that's going to give us the slope of the line at an instant, the line tangential to the curve. The slope of the line at that instant is going to give you your instantaneous velocity. Uh, and then that's just rather than being solely dependent on like what your displacement looks like, or being dependent on uh your final minus your initial values without worrying about anything in between. This allows you to worry about everything in between. It allows you to treat velocity as a function of time and see where how fast you're moving and like how fast you're going as the time goes by. So, oh, I hope I saved that. Yep. Uh, so V instantaneous is the slope of the line. So, for example, if we have a very jagged line, then uh, position versus time, then what we would find if we were talking about the old way, if we were talking about delta x over delta t, the displacement over time, is that we would find that it doesn't really give us a good idea of what's happening, but each line segment is going to have a slope. And because the line segments are constant slope, that means that the velocity is a constant velocity over the uh, course of this from this point to this point, or from this point to this point, or from that point to that point, that point to that point, that point to that point, or that point to that point. Each of them is going to uh, give you a constant velocity, v 4 time which is going to give you eventually the average velocity, but we're not going to worry about that right now, because uh, yeah, just because we're not caring about the average velocity right now. Right now, we only care about the instantaneous velocity because the instantaneous velocity is the more interesting quantity because it tells us what's going on at a given time. So you can find the velocity at here, here, all of these things, and you can find the velocity by finding the slope of the line segment. So x1 minus x naught over t1 minus t naught for this first line segment, where this is x or t1, t naught, t2, t3, and so on and so forth. So that is the equals v first line segment. This is the v of the second line segment, which is going to be x2 minus x1, the position at time 1 versus the position at time 2 over t2 minus t1. And then this is kind of getting complicated to write out, but this is the velocity of the second line segment. And then For the purposes of making this more easily readable, I'm just going to erase everything except for the most necessary thing. Okay, so that's just what that looks like. And then if you were to draw a velocity versus time graph, so if you drew a v versus time graph, then it would look something like dot 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 this, where these values, these are the constant velocities in those time intervals. Where we talked about having a constant velocity from here to here, and then a constant velocity from here to here, from here to here, and from here to here, and so on and so forth. Well, each of those constant velocities is just the slope of that line at some time, and that's going to give you yeah, it's just going to give you constant velocities with discontinuities every time there's a giant there's just like a snap in the line segment, so that it starts out at one slope then suddenly at another slope, then that's a discontinuity at that position. But each of these plateaus here gives you the velocity, the slope of that time interval that we're talking about. And then if we were talking about speed, versus time, then it would just be the absolute values of all of these velocities. Okay, so hopefully that's clear. I went a little more into detail than I was expecting, but hopefully that clarified a few things for you. So if velocity is the change in position over time, the displacement over time, then acceleration equals delta V over delta T, which is the change in velocity over time. And A instantaneous is equal to dV dt, which is equal to d squared V, or d squared x dt squared, because it's the double derivative of a position over time because it's the derivative of position over time. So, like I said, same rules apply as velocity. It's not anything different. It's just saying that this is the change in the change of position over time, which is the change in position over time. So that's that. One last thing I want to note before we just get into the kinematics equations and being able to solve things is that uh, having you can have negative velocity or you can have negative acceleration, but that doesn't mean that the position is going to be negative or the acceleration is going to be negative or the velocity is going to be negative if you have a negative acceleration. All that means is that for negative acceleration, you start out, oh, that's a terrible line. If you start out going 70 meters per second and have an acceleration of -2 meters per second squared, then as enough time passes, you're still going to be going forward at say 10 meters per second. Uh, but the change, it's going to be a negative change in velocity. So it's going to be a smaller velocity than you had before. So uh, V final minus V initial over delta t equals negative me uh being negative only means that your initial velocity is going to be bigger than your final velocity if both are positive. And then the same thing uh if both are negative, or if it is a negative number is your final or initial velocity, then that means that it's going to be getting faster because you're accelerating in the negative direction. So you're getting faster in the negative direction. So if you have at some point it slows down to zero and starts going backwards, then this velocity, -10 meters per second, is eventually going to get faster and faster because your acceleration is going to be in the negative direction, which means that it's accelerating in the negative direction. Oh, I forgot my squared here. -2 meters per second squared. So it's accelerating in the negative direction, which means that if the velocity is in the positive direction, then it's slowing down. But if the velocity is in the negative direction, then it's speeding up in the negative direction. Hopefully that makes sense. And the same rules are going to apply to position versus time with a negative velocity. So if you're uh 20 miles to the east and you're going uh or no, west is, yeah, east is positive x generally. If you're 20 miles to the east and you're going negative 20 miles per hour, uh then that means that you're still east of your starting point, but you are getting farther and farther to the west as time goes on. And if you start out 20 miles to the west and you're going negative 20 miles per hour, then that also means that you're just going farther and farther to the west. You're going from 20 miles to the west to 40 miles to the west. But if you start out to the east, then in half an hour you would go from 20 miles to the east to only 10 miles to the east. And then hopefully that makes sense to y'all. I can go over it again in class if you need to, or you can go over the books or just shoot me an email and I'll be available for you. So, kinematics. Kinematics is the study of motion. So, what we're going to do in this case is we're usually going to have constant acceleration. So A equals uh, the average acceleration, which is equal to a constant. So if that's the case, then V A of t equals A. V of t is going to be A of t dt from t naught to t, or to t final. Let's call it t final so we don't mix up our variables. Equals t naught to t final A dt, which if you don't know how to do, we have the derivative of a polynomial function d dt of a t to the n is equal to n times a t to the n minus 1. So as long as this is definitely something that you should remember from calculus, but as long as your variable that you're taking a derivative is some constant times t to some constant, which is in this case n, then the derivative is just going to be that second constant n times a, the constant, the multiplicative constant, times t to the n minus 1, which means that going backwards, if you have b, if you're taking the integral, the indefinite integral of b t to the m dt, then that's going to be equal to b over m plus 1 t to the m plus 1. So if you have some, so you're just doing the same thing as taking the derivative, but doing it backwards. So instead of going the t value going down, by one value, it goes up by one value. And then instead of timesing whatever a polynomial value you have times the constant, you divide by whatever polynomial you end up with. And that's just going backwards. It's getting the right values, or it's just doing the same thing as we were talking about with the derivative. It's just doing it in reverse because that's what uh or that's what derivative does. So if we take, or that's what integral and derivative are to each other. So in the same way that you multiply and divide, and that's going to give you the same value, if you integrate and take the derivative, that's going to give you the same value. So if we just try this out, then this is going to be integral of a times t to the a t to the n minus 1 dt. Uh, so it's the derivative of a n times a times t to the n, or sorry, excuse me there. It's the derivative of a times t to the n, and if you uh do this again, uh, if you take this derivative, it gives you this value, and you're integrating that. So in this case, if you integrate that, then you have n a, which is our b value going over here, t to the n minus 1, where n minus 1 is our m value, dt. That is going to be equal to na divided by n minus 1 plus 1, because this is m plus 1, t to the n minus 1 plus 1, which is just going to be equal to a t to the n. So we derive it, or we take the derivation of it, and then we integrate it, and it gives us the same value that we initially had. So in this case, v of t is equal to a, where is my cursor? There we go, is equal to t naught to t final a t to the 0, because t to the 0, any value to the 0 is just going to be equal, uh, yeah, it's just going to be equal to t to the, or any value to the 0 is equal to 1, is what I'm trying to say. So equals t naught to t final a t to the 0 dt, which is going to be equal to a t to the 1 from t naught to t final, which is equal to a t final minus t naught. Or if we define t naught to be equal to 0 and t final to be equal to t, then V of t equals A times t. And then do the same thing again. X of t equals integral of V of t dt equals plus V naught. I forgot the constant. You always have a constant, remember? So the constant when you integrate is just the value as t equals 0, which is called V naught, where V naught is the value as t equals 0. So x of t, the position of t as t goes on is going to be equal to A times t plus V naught dt, which is equal to 1/2 AT squared plus V naught t plus x naught. So these are our first two kinematics equations. For constant, acceleration, these are the first two kinematics equations. And that's going to be helpful if we know t, know t or can solve for t. But what our final kinematics equation basically, I think there might be one more that's skipping my mind right now, but I'll check in a second, is if you have x of t equals 1/2 AT squared plus V naught t plus x naught, and then V of t equals AT plus V naught, then what you want to do is, if you don't want to solve for time every time that you do an equation, you can just use these two equations and solve for time with one of these equations, and then plug that into the other time in order to uh, find the value or find an expression for V naught, X naught, and A uh, based only based only on V naught, X naught, and A, and V final, instead of having to worry about time all the time. So V final equals V of t equals AT plus V naught. So V final minus V naught equals AT. T is equal to V final minus V naught over A. And then that's just coming from here. Then you plug this t into this equation. So x final equals x of t equals 1/2 AT squared plus V naught t plus x naught equals 1/2 A times V final minus V naught over A squared plus V naught times V final minus V naught t or not t over A plus x naught. So x final minus x naught. So all I did was, if you have trouble following the algebra, all I did was plug in this t into here and here. And then subtract by x naught on both sides. So x final equals 1/2 a times v final squared plus v naught squared minus 2 v final v naught over a squared plus v naught times v final minus v naught times v naught over a, which is going to be equal to 1/2 a v final squared, or 1/2 1 over 2a times v final squared plus v naught squared minus 2 v final v naught plus v naught v final minus v naught squared over a, which if you do all the algebra, you just finish that up, it's going to give you 1 over 2a v final squared minus v initial squared. So you are able to solve for x final minus x naught based on the final and initial velocities as well as the acceleration with no uh need to plug in time. So this is going to be our third kinematics equation. If you give me a second, I think there's a fourth one that I always forget about. Uh, yeah, sorry, my lecture notes were too bulky for my phone app to use, so I have to go directly to the textbook right now. Oh, and yeah, that's the main ones, but another couple of kinematics equations are that x final, or x of t, or x final, let's just say, equals v bar t plus x naught, and v bar equals v final minus v naught over 2. So that's pretty simple to derive. Those are pretty simple to derive. You just need to do a little algebra to them, which doesn't, I'm going a little, I've been rambling for a while, so I don't think that I'm going to do that, but v bar, the average value of v being v final minus v initial makes sense as with a constant acceleration, then velocity is just going to be a straight line. The midway point And if you cut a straight line in half, then that's going to have as much of the line to the right half as you do to the left half. So that's going to give you V bar equals V final minus V initial over 2, where the average value is just the simple average value of two numbers. Yeah. And then, oh no, what happened? My board. There we go. So I'm going to do one. I'm going to do one example, and then I'm going to move on to free fall, and then that's going to be the lecture. So if you have a gazelle, a cheetah, and a gazelle, and the cheetah surprises the gazelle, so that they both have the same initial position. Uh, so cheetah just pounces on the gazelle, but misses, and then the gazelle starts running. So if in this case, X final, what we're going to assume for the gazelle is that it gets all of its energy, or it gets all of its velocity straight away, but it has zero acceleration. And then it also starts from a point 0. Then that's going to give us the equation X final of gazelle equals V naught gazelle times T. So that's just going to be one of our we're going to have two equations for the motion of the gazelle and the cheetah. And then this is just the equation of motion for our gazelle. This is how we define it. It has no acceleration and it has no initial position because both the cheetah and the gazelle start from the same initial position. So that is going to be equal to 1/2 AT squared plus 0 plus V naught T. A is 0, uh, X naught is 0. So it just ends up being V naught G times T. And then X final cheetah, we're going to assume the opposite is true, where it doesn't have any initial velocity, but it does have an acceleration. So 1/2 A cheetah T squared plus yeah, 1/2 A cheetah T squared uh plus 0 times T, because there's no V naught cheetah, plus 0 because we define X naught cheetah to be equal to X naught gazelle is equal to 0. Then this is going to be 1/2 AC T squared. So what we want to know is we first want to know what time it takes for the cheetah to catch up to the gazelle. And we also want to know what the final distance is going to be for that. So if we do this, Then x final cheetah is going to be equal to x final. Okay, I keep clicking on the button accidentally. X final gazelle, because that's going to be the point where they both catch each other, right? So 1/2 AC t squared is going to be equal to V naught G T, or 1/2 AC T equals V naught G T equals V naught G divided by 1/2 AC equals 2 V naught G over AC. So that's how long it's going to take. Uh, I'm not going to plug in any numbers because once you get far enough in physics, you don't like numbers. You like it to uh, be as generalizable as possible for a given problem, but also just because I don't have a calculator right now, so I don't want to try to do this in my head. But T equals 2 V naught G over AC. And then that's just going to be the time when X final equals X final for the gazelle and the cheetah. And then plug this in for X final cheetah equals 1/2 AC times 2 V naught G over AC squared. And that's going to give you 1/2 AC times 4 V naught G squared over AC squared is just going to be equal to 2 V naught G squared over AC. And then we were able to divide through by T. Earlier, I didn't bring this up, but because we assumed that time was going to be positive, so we didn't have to worry about T squared being a negative value, or T squared giving you a positive value for a negative uh, time. So this is X final cheetah. And then if we look at X final gazelle, then that's just equal to V naught G times T, which is 2 V naught G over AC, which is again equal to 2 V naught G squared over AC. So both of these come out with the same final answer, which means that we did the math right. If you want to check your math in a homework problem and you're having issues, then a good thing to do is to just go backwards from the problem. So the final thing that we're going to do is work through our first part of actual physics, actually, because everything we've been doing so far is saying is just how anything would move without knowing anything about the laws of the universe. If we had a constant acceleration, if we had a velocity and position, then without knowing anything about the laws of the universe, you wouldn't say that with a constant acceleration it moves like this. But the first piece of actual physics that we're going to do is on the face of the Earth, acceleration due to gravity is a constant. So I talked about this a little in lab, but I haven't talked about it in lecture. So acceleration due to gravity is constant. So the value of acceleration from gravity is called g, and it's going to have a value of 9.8 meters per second squared, which again, we've been dealing with that. We've been talking about that in lab, but we've never brought it up in lecture, and we're going to actually get to what that means. So the acceleration towards due to gravity is some constant pointing down towards the center of the Earth. And this is true for other celestial bodies or planets or moons where the radius of the body is going to be much bigger than the radius of what you're dropping. So we just say that g equals 9.8 meters per second squared because that's true on the surface of the Earth, but on the surface of the moon, it's going to be a different value. On the surface of Mercury, I don't think Mercury has a surface now that I think about it. It's going to be a different value. But on the Earth, when we drop something, it has an acceleration of g equals 9.8 meters per second squared. So, uh, yeah, that's basically all that I have to say about it. It is constant for any object. So up until Galileo, we thought that heavier objects fell faster, but that's just because of air resistance. If you go into a vacuum or if you go into someplace with a lot without a lot of air, then the objects are going to fall at the same rate and reach the ground. Two objects that you drop are going to reach the ground at the same time. So this is the only physics that we've done so far. And this is the first physics, and this is all that I need to say about this uh is already on the uh is already on the that or is already uh on the PowerPoint. So we're going to get more into physics next week, but for the time being, this is it. And I'm just going to do a quick demonstration. It's the same exact rules as what we were following before for objects in free fall. So if this is an object in free fall, if we throw something up into the air with some velocity v naught, then how high up into the air is it going to go? So the acceleration due to gravity is going to slow down this v naught. It's going to keep slowing down the velocity over time until it stops and it starts going the other way. So the highest point that you're going to reach is going to be right when it stops right when velocity equals 0, right before it starts going the other way. So v final squared minus v initial squared is going to be equal to over 2 times acceleration is equal to x final minus x initial, which in this case we're going to call these y because it's pointing up and down rather than side to side, which is going to be equal to y final if we decide this equals 0 equals y final. Okay? So y final is what we're trying to solve for. And we know v final initial equals negative v or is equal to 0. So it's negative v naught squared over 2 times negative g, because acceleration is pointing in the opposite direction. It's pointing down. So it's going to have a value of negative g rather than positive g, which is going to be equal to v naught squared over 2g, where g is the 9.8 meters per second squared. So this is going to tell you how high a ball will go if you throw it into there with some velocity v naught. So uh that's the only physics we're doing today. So I'm just going to really quickly if you have some equation x of t equals uh 5 times t cubed plus 2 times t, then the velocity of this is just going to be equal to dx of t dt is equal to 5 times 3t squared plus 2, where these are in units of meters per second, and then t is in units of seconds. Oh, this is meters per second cubed. Uh, so yeah, that's just some constant 5 meters per second cubed times 3t squared uh plus 2 meters per second is going to give you your velocity over time versus x of t. And then if you have that equation, then a of t is equal to dv dt is equal to uh 5 times 3 times 2t, where 5 is a is 5 meters per second cubed, and t is in terms of seconds. And then these are just numbers. Okay. So yeah, I just realized that I didn't really go into that, but I think that that's something that you should be able to figure out for yourself if you're given a polynomial value and knowing what the derivative of a polynomial is. You should be able to figure these out for yourself. So that went on for a while. Sorry, like I said, the main thing that we just learned is what a derivative is and like what the kinematics equations are. So hopefully that shouldn't be too much of a bother, or I didn't bother you too much with this. You can reach out to me over office hours, or I don't have office hours, but you can reach out to me over email or on Canvas or anything like that, and I'll be there for you. All right. Thank you very much. I hope you have a nice weekend.